Between the radiant galaxies lies a space seemingly empty, yet filled with mysteries. Intergalactic space, though faint and difficult to observe, occupies most of the universe's volume, hiding crucial pieces of the puzzle of cosmic formation and evolution. What makes this space so special? Intergalactic space is often described as the vacuum of the universe, but in reality, it is not entirely empty. Although one of the rarest and most inaccessible environments, intergalactic space contains trace amounts of matter, creating a unique ecosystem that plays a crucial role in the universe's evolution. The density of matter in intergalactic space is unimaginably low. With less than 1 atom per cubic centimeter, it is the sparsest region known to humanity. For perspective, Earth's atmospheric density is approximately 119.1 times 10 to the power of 19 molecules per cubic centimeter, making intergalactic space millions of trillions of times less dense. Yet, the presence of these solitary atoms is sufficient to form significant physical and chemical structures that shape the interactions between galaxies and galaxy clusters. Most of the matter in intergalactic space consists of ionized gas particles, primarily hydrogen and helium, the simplest and most abundant elements in the universe. These elements are remnants from the early stages following the Big Bang, when the universe was young and matter existed mainly in its primordial state. In addition to hydrogen and helium, heavier elements like carbon, oxygen, nitrogen, and silicon appear in trace amounts. These elements are typically released through supernova explosions or interactions between galaxies, enriching the chemical diversity of this otherwise barren environment. Intergalactic space is also the primary path through which light from distant galaxies travels to Earth. However, this light is often scattered or absorbed by ionized gas particles within intergalactic space. This process creates dark regions, or voids in observational data, making it incredibly challenging to study these distant areas. Astronomers use sophisticated techniques, such as analyzing the spectra of light from quasars, to infer the composition and density of matter in intergalactic space. Additionally, intergalactic space is influenced by radiation from high-energy sources, such as supermassive black holes, or galaxy clusters emitting X-rays and gamma rays. This radiation can further ionize hydrogen and helium atoms, creating heated gas regions with temperatures reaching millions of degrees Kelvin. These regions act as reservoirs of matter and supply material for star formation processes within galaxies. Though seemingly empty and insignificant, intergalactic space is a critical link in the cosmic web. Here, large-scale interactions occur, connecting galaxies and galaxy clusters through gravitational forces and streams of matter. These gas streams can stretch millions of light-years, forming colossal cosmic filaments, the largest structures known in the universe. In conclusion, intergalactic space is far from being a meaningless void. It holds essential pieces of the universe's history, serving as the foundation for galaxy formation and evolution. Exploring the physical properties of this space not only enhances our understanding of large-scale cosmic structures, but also unveils hidden secrets about the origins and fate of the vast universe we inhabit. Intergalactic space is not a uniform environment, and one of its most notable features is the presence of intergalactic gas clouds. These are regions where matter concentrates with diverse densities and temperatures, forming complex structures that play an essential role in the universe's operation. These clouds are not merely reservoirs of matter, but also witnesses to significant cosmic events, from the Big Bang to the present day. Intergalactic gas clouds exhibit a wide temperature range from extremely cold levels near -270 degrees Celsius to millions of degrees Kelvin. The temperature of these clouds largely depends on their location in the universe and nearby energy sources. Clouds near active galaxies or high-energy sources like supermassive black holes often have higher temperatures due to exposure to X-rays and other high-energy radiation. Conversely, clouds in remote areas, less affected by external energy, may maintain extremely low temperatures, nearly frozen in the frigid intergalactic environment. Scientists have used telescopes and spectral analysis techniques to study the chemical composition of these gas clouds. They have discovered that, although hydrogen is the dominant component, as it is the most common element in the universe, these clouds also contain heavier elements like oxygen, silicon, and carbon. These elements result from the formation and evolution of stars within galaxies and are released into space through supernova explosions or intense galaxy interactions. These chemical fingerprints not only provide insights into the origins of matter in the universe, but also reveal how galaxies interact and exchange material with each other. One of the most critical roles of intergalactic gas clouds is connecting galaxies within the cosmic web. Some gas clouds do not exist in isolation, but extend into large streams of matter, forming bridges between galaxies. These gas streams, known as cosmic filaments, act as conduits for the transfer of matter and energy between galaxies. Through these streams, material from one galaxy can move to another, sustaining cycles of regeneration and fueling ongoing star formation. These cosmic filaments also shape the macroscopic structure of the universe, linking galaxy clusters into an expansive network that spans vast stretches of space. Beyond their physical and chemical roles, intergalactic gas clouds contain vital clues about the universe's history. They are remnants of significant events such as the Big Bang, which created the first hydrogen and helium. Simultaneously, they record traces of supernova explosions, galaxy collisions, and the formation of large cosmic structures. By examining the composition and distribution of these clouds, scientists can reconstruct a timeline of how the universe has evolved from its early stages to the present. In summary, intergalactic gas clouds are not merely concentrations of matter, but key to understanding the universe's functioning and evolution. With their ability to connect galaxies, provide critical material resources, and preserve records of pivotal cosmic events, these clouds are indispensable pieces in the grand puzzle of intergalactic space. Studying them not only expands human knowledge of the universe's large-scale structures, but also inspires exploration of the deepest mysteries of the vast cosmos. Intergalactic space, which at first glance might seem like a meaningless void between galaxies, actually plays a fundamental role in shaping and operating the universe. It serves not only as the substrate connecting all large-scale structures, but also as the environment that determines the formation and evolution of galaxies, galaxy clusters, and the vast cosmic web. While galaxies, stars, and planets capture attention with their brilliance and dynamism, they account for only a small fraction, about 10%, of the universe's total mass. The majority resides in intergalactic space, an area seemingly invisible, yet containing nearly all the matter in the universe. Intergalactic space can be considered the scaffolding that keeps the universe functioning, linking galaxies and maintaining balance within a complex network stretching billions of light years. One of the most critical features of intergalactic space is the presence of primordial gas particles, primarily hydrogen and helium, the first elements formed after the Big Bang. These gas particles, existing almost unchanged over billions of years, are regarded as living fossils, recording the universe's early stages. Scientists study their composition and distribution to gain a clearer understanding of the moments immediately following the Big Bang. These gas particles are not only evidence of the universe's origins, but also essential for forming new galaxies and stars. Intergalactic space is also where material exchange between galaxies occurs. Long, slender streams of gas connect galaxies, forming a three-dimensional cosmic web. This network not only determines how galaxies are distributed in space, but also governs their interactions. For instance, material from one galaxy can transfer to another via intergalactic gas streams, providing the resources necessary for star formation. This process sustains the vibrancy of galaxies and plays a pivotal role in the universe's matter cycle. Additionally, gravitational forces within intergalactic space contribute to shaping the universe's largest structures. High-density regions in this space attract surrounding matter, forming massive galaxy clusters, while lower-density areas create cosmic voids. This distribution and interaction create a highly diverse and intricate cosmic tapestry, where every galaxy and cluster is interconnected within the broader network. Most importantly, intergalactic space underscores that even the emptiest regions contain irreplaceable scientific value. It is the repository of the universe's origin story, the setting for critical processes influencing the entire cosmos, and the key to unlocking humanity's understanding of the universe's deepest mysteries. Research into this environment not only reveals how the universe formed and evolved, but also opens new possibilities for deciphering the fundamental laws of nature. In conclusion, intergalactic space is far more than the empty space between galaxies. It serves as a foundational environment, connecting large-scale structures, driving matter cycles, and preserving the precious legacy of the universe's history. From these empty regions, we can uncover answers to humanity's most profound questions about existence in the vast expanse of the cosmos. In the vast expanses between galaxies, where it seems like nothing exists but endless void, silent streams of gas interconnect the universe. These intergalactic gas flows not only sustain the vitality of galaxies, but also serve as the lifeblood, nourishing the cosmos over billions of years. What makes them an indispensable part of the universe's structure? Intergalactic gas, though scarce and difficult to detect, plays an essential role in star formation, ensuring galaxies continue to evolve and maintain their vibrancy over billions of years. These seemingly faint streams of gas serve as the primary source of material, sustaining the universe's cycle of perpetual renewal. Gravity is central to drawing intergalactic gas into galaxies, where it becomes raw material for star formation. Galaxies, with their powerful gravitational pull, not only maintain the cohesion of stars, planets, and matter within, but also attract gas particles from intergalactic space. Once these gas clouds are pulled into a galaxy, they often condense into denser regions, where conditions become ideal for new stars to form. These young stars, typically bright and energetic, rejuvenate the galaxy and promote its development. The rate at which material flows from intergalactic space into galaxies is a critical factor in star formation. On average, intergalactic gas streams supply a galaxy with material at a rate of about 1 solar mass per year. This is also the estimated star formation rate in the Milky Way, highlighting a close relationship between the influx of intergalactic gas and a galaxy's ability to sustain its creative processes. These gas streams are not just supplementary, but essential to preventing galaxies, especially spiral galaxies, from exhausting their star-forming material. For galaxies like the Milky Way, intergalactic gas plays a crucial role in ensuring sustainable growth. Young stars, typically found in the spiral arms, where star formation is most active, are nourished by this resource. Without a continuous inflow of gas, galaxies would eventually deplete their internal reserves and lose the capacity to form new stars. This would not only reduce the galaxy's vibrancy, but also impact the structure and balance of the entire cosmic ecosystem. Beyond sustaining star formation, intergalactic gas also plays a vital role in connecting galaxies. The streams of gas stretching between galaxies act as bridges, facilitating the transfer of material and gravitational interactions between cosmic structures. These gas flows contribute to the formation of the vast cosmic web, where galaxies are bound together in a colossal three-dimensional framework. The absorption of intergalactic gas into galaxies is also a testament to the universe's ongoing process of renewal and regeneration. The young stars born from this material often shine brilliantly, actively shaping the galaxy's structure. Over time, as older stars fade away, intergalactic gas continues to replenish the energy needed for a new generation of stars, maintaining balance and momentum for the entire galaxy. In conclusion, intergalactic gas is not only the raw material for star formation, but also a critical factor in sustaining the vitality and evolution of galaxies. Thanks to these gas flows, galaxies like the Milky Way can continue producing stars, preserving their brilliance and place within the vast cosmic web. Studying and understanding the role of intergalactic gas not only expands human knowledge of the universe, but also illuminates how galaxies sustain their existence over billions of years. Intergalactic space, though seemingly an empty void, actually contains a complex and dynamic network where streams of gas connect galaxies within a structure known as the cosmic web. These are not merely bridges, but vital arteries that sustain the universe's vibrancy and growth, while offering profound insights into how galaxies interact and evolve. The cosmic web is composed of immense intergalactic gas streams, forming invisible bridges linking galaxies. These streams not only transport material, but also act as conduits for energy, balancing gravitational forces and stabilizing large-scale cosmic structures. In this network, galaxies do not exist in isolation, but are intricately interconnected in a dynamic system where matter and energy continually circulate, creating an endless cycle of renewal. The role of intergalactic gas flows is akin to the circulatory system in a living organism. They transfer material from one galaxy to another, replenishing the resources necessary for new star formation and maintaining internal activity within galaxies. This is especially significant in galaxy clusters, where frequent interactions between galaxies occur. In such environments, intergalactic gas streams not only supply material, but also act as catalysts for large-scale cosmic phenomena, such as the formation of star clusters or the restructuring of galaxies after collisions. In addition to providing material, intergalactic gas streams profoundly influence the structure and development of the universe. They help scientists better understand how galaxies interact and evolve within a complex, interconnected system. For example, during galaxy collisions or mergers, these gas flows serve as critical witnesses, recording changes in structure and material distribution. When two galaxies collide, the gas is compressed to create regions of intense star formation while also redistributing matter across galactic systems, producing novel structures. These gas streams are not just material bridges, but also cosmic glue that binds galaxies together, ensuring they are not isolated in the vast expanse of space. Their presence demonstrates a universe in constant motion and connection. Through these streams, galaxy clusters and even distant galaxies remain tightly bound, contributing to a vast cosmic web spanning billions of light years. Intergalactic gas flows are also key to unraveling major cosmic mysteries. They enable us to explore the origins and distribution of dark matter and provide deeper insights into gravitational forces and their impact on galaxy formation and evolution. By studying this network, scientists have reconstructed parts of the universe's macrostructure, where every component, from the largest galaxies to the most tenuous gas streams, is intricately linked within a harmonious framework. In summary, intergalactic space, with its intricate gas flows and extensive network of connections, forms the foundation of the universe's operations. These streams not only transport matter and energy, but also act as bridges between galaxies, ensuring that the universe maintains balance and growth. In humanity's quest to explore the cosmos, understanding intergalactic gas flows not only brings new knowledge, but also sheds light on how the universe's largest structures function and interconnect. Intergalactic gas, though seemingly quiet and unnoticed, is the product of dynamic and intense processes in the universe. These gas flows are not merely evidence of continuous interactions between galaxies and their surroundings, but also carry the story of the formation and evolution of galaxies over billions of years. One of the primary sources of intergalactic gas is supernova explosions. When massive stars exhaust their fuel and reach the end of their life cycles, they explode in dramatic events, releasing vast amounts of material into space. Some of this material, rather than being retained within the galaxy, is expelled due to the immense energy of the explosion. These gas streams contain heavy elements like carbon, oxygen, and iron, the products of nuclear fusion within stars before they exploded. As a result, intergalactic space becomes chemically enriched, providing raw materials for the formation of new stars and other galactic structures. In addition to supernova explosions, intergalactic gas forms through dynamic processes involving supermassive black holes and galaxy collisions. Supermassive black holes at the centers of active galaxies emit massive radiation, capable of expelling gas and dust from the galaxy at tremendous speeds. These galactic winds not only reduce gas density within galaxies, but also contribute to intergalactic gas reservoirs, creating streams of matter extending millions of light-years. Similarly, when two galaxies collide, the immense energy generated can eject significant amounts of gas into intergalactic space. This continuous recycling and replenishment keep intergalactic environments rich in energy and matter. These intergalactic gas streams play a role beyond the physical transport of material. They also serve as witnesses to the universe's history. They carry valuable information about the chemical composition and major events within galaxies, such as supernova explosions, black hole activity, and galaxy collisions. By studying these gas flows, scientists can trace the evolutionary stages of galaxies, from star formation to structural reorganization after collisions. The diverse origins of intergalactic gas reveal that it is not merely a byproduct of astronomical processes, but an integral part of the universe's matter cycle. These gas flows continually participate in material regeneration, maintaining the balance and growth of galaxies. They also act as bridges between galaxies, contributing to the construction of the vast cosmic web where all structures, from galaxy clusters to cosmic filaments, are tightly interconnected. More importantly, intergalactic gas shows us that the universe is not a collection of isolated galaxies, but a unified and interconnected system. Through these gas flows, matter and energy circulate, driving the continuous evolution of galaxies and cosmic structures. Studying intergalactic gas not only helps humanity understand the origins and development of galaxies, but also reveals the fundamental laws governing the universe's operation. In conclusion, intergalactic gas is a crucial component of the universe, not only recording grand cosmic processes, but also sustaining the vitality and growth of galaxies. These gas flows, with their rich origins and profound impacts, are a vivid testament to the unending connection between the components of the vast cosmos. In the vast universe, galaxies are not isolated islands, but are constantly interacting through gravitational forces. From exchanging material to regenerating and destroying, these invisible connections have shaped the evolutionary history of the cosmos over billions of years. What happens when galaxies draw material towards themselves, and how do they sustain their endless cycles of renewal? Gravity, one of the four fundamental forces of the universe, plays a central role in driving the movement and exchange of material between galaxies. Thanks to gravity, galaxies are not independent entities, but exist in a tight-knit web of connections that contribute to the formation and maintenance of the universe's complex structure. In intergalactic space, galaxies are not static entities, but are constantly influenced by each other's gravitational pull. This interaction generates massive streams of material, stretching millions of light years, moving between galaxies. These streams consist of gas, dust, and even stars torn away from their parent galaxies during interactions. They act as physical bridges between galaxies while redistributing matter and energy on a cosmic scale. This illustrates how gravity, despite being invisible, governs and orchestrates the largest-scale activities in the universe. One of the most significant contributions of these material streams is providing raw materials for new star formation. When clouds of gas or wandering stars are pulled into a galaxy by gravity, they often concentrate in high-density regions where conditions become ideal for star formation. Large gas disks formed by these material streams create perfect environments for gas clouds to collapse, triggering bursts of star formation activity. The young stars born from these gas streams not only increase the galaxy's mass and vibrancy, but also help reshape its structure. The Milky Way is a prime example of material exchange between galaxies. One of the most notable phenomena is the Magellanic Stream, a massive stream of material extending from the Milky Way's two satellite galaxies, the Large and Small Magellanic Clouds. This stream, consisting of millions of solar masses of hydrogen, is moving towards the Milky Way and may become a crucial resource for future star formation. The interaction between the Milky Way and its satellite galaxies not only supplies material, but also generates powerful gravitational effects, shaping the orbits and structures of the galaxies involved. Material transfer between galaxies is not limited to satellite systems. It also occurs on larger scales, especially in galaxy clusters, where hundreds of galaxies interact. In such environments, gravitational forces not only strip material from member galaxies, but also form massive bridges of matter, linking entire clusters into interconnected systems. These material streams also help redistribute mass among galaxies, ensuring the stability of galaxy clusters over billions of years. These processes are not just physical phenomena, but also provide deep insights into the evolution of the universe. They demonstrate that galaxies are not isolated systems, but are constantly interacting, exchanging material, and relying on each other. This material movement sustains the universe's cycle of regeneration, from replenishing star formation material to reshaping large-scale cosmic structures. In conclusion, the transfer of material between galaxies not only highlights the role of gravity, but also underscores the interconnected and interdependent nature of the universe. Streams of gas, dust, and stars are not merely random fragments, but essential components of the grand cosmic evolution, where everything is in motion, interaction, and constant renewal. Matter in the universe is not a static entity, but is continuously recycled through cyclical processes, ensuring the growth and maintenance of galaxies over billions of years. This cycle not only preserves balance, but also creates opportunities for galaxies to restructure and evolve, transforming them into dynamic and vibrant systems. A significant part of the universe's matter recycling cycle begins with intergalactic gas, a primary source of material for galaxy development. Under the influence of gravity, massive gas clouds from intergalactic space are drawn into galaxies, concentrating in high-density regions such as gas disks or galactic centers. These gas streams not only provide the raw materials for forming new stars, but also contribute to the creation of vital structures like spiral arms or young star clusters, injecting energy and vitality into galaxies. This process clearly demonstrates that the universe is constantly in motion and renewal, ensuring that no resource goes to waste. However, the recycling cycle is not limited to drawing material into galaxies, but also involves expelling material outward. Supernova explosions, cataclysmic events marking the end of massive stars, are among the primary sources of expelled material. These explosions release vast amounts of gas and dust, along with heavy elements like carbon, oxygen, and iron, forged through nuclear fusion in the star's cores. Similarly, stellar winds from massive stars contribute to ejecting material into intergalactic space, forming streams that stretch millions of light years. These material flows not only chemically enrich intergalactic space, but also provide resources for forming the next generation of stars and galaxies. The combination of these two processes, pulling material in and pushing material out, ensures that the universe's matter recycling cycle never ceases. This cycle functions like a cosmic circulatory system, where every particle of matter is reused to sustain the vibrancy and growth of galaxies. Stars, after depleting their fuel and reaching the end of their life cycles, do not simply vanish, but leave behind material legacies in the form of gas and dust. This material then re-enters the recycling cycle, becoming raw material for new stars or helping restructure galaxies. A prime example of this process is the role of intergalactic gas streams in sustaining the Milky Way's growth. The Milky Way continuously receives gas streams from intergalactic space, such as the Magellanic Stream, originating from the large and small Magellanic Clouds. These streams not only enrich the galaxy's internal resources, but also play a crucial role in fueling star formation in the spiral arms, the most dynamic regions of the galaxy. Thanks to this recycling cycle, the universe never stops moving and renewing itself. From the explosive power of supernovae to the faint streams of gas moving through intergalactic space, everything is recycled and reused in the grand cosmic cycle. This process not only maintains the stability and growth of galaxies, but also creates richness and diversity in their evolutionary paths. It is a testament to a universe in perpetual motion, where every resource is fully utilized to create an ever-changing and evolving cosmic tapestry. Gravity plays an irreplaceable role in sustaining the motion, structure, and evolution of galaxies, shaping the universe as we see it today. More than just holding stars in galaxies or maintaining their orbits, gravity is a driving force that creates, destroys, and reshapes galaxies over billions of years. Gravitational interactions not only establish balance, but also drive significant development and transformation in cosmic structures. One of gravity's most important roles is shaping galaxy structures. Spiral galaxies, like the Milky Way, maintain their balanced forms thanks to gravitational interactions with nearby galaxies. This force ensures that spiral arms retain their structure, and that stars, planets, and other matter within the galactic disk move in coordinated motions. In contrast, irregular galaxies are often distorted by collisions or mergers with other galaxies. These encounters can lead to fragmentation or fusion, completely altering their shapes and characteristics. Beyond shaping structures, gravity is a catalyst for forming new galaxies through galactic collisions. When two galaxies meet, they are not simply destroyed, but often merge to form a larger and newer galaxy. This process is frequently accompanied by bursts of star formation. Millions of new stars can emerge from the compressed material after a collision, causing the merged galaxy to shine brightly for hundreds of millions of years before stabilizing. However, gravity is not always constructive. On larger scales, gravitational forces within galaxy clusters can tear apart smaller galaxies. In these clusters, where thousands of galaxies coexist, gravitational competition is intense. Smaller galaxies may be pulled into larger galaxies, becoming part of them or even being completely destroyed. This process contributes to the mass and scale growth of larger galaxies while reducing the prevalence of smaller galaxies in the universe. Gravitational interactions do not just impact individual galaxies, but also shape the cosmic web, a structure consisting of long filaments connecting galaxy clusters. These filaments concentrate high-density matter, while the voids between them are nearly empty. Gravity pulls matter towards the filaments, making them denser over time. This is how the universe has evolved from initially uniform gas clouds into the complex structure we observe today. Gravity's role extends to sustaining life and advancing scientific exploration. It allows planets to maintain stable orbits around their stars, creating the necessary conditions for life to develop. Additionally, studying gravity in the universe helps scientists uncover mysterious phenomena like black holes, gravitational waves, and dark matter, key factors in understanding the origins and fate of the universe. Gravity is not only a driving force, but also the architect of the universe. From stabilizing galaxies to shaping massive structures like the cosmic web, gravity is the central factor in all processes of motion and evolution in the cosmos. Its extraordinary and powerful influence allows us to marvel at the spectacular wonders of astronomy today. When looking into the vast universe, galaxies stand out with billions of stars shining brightly. However, not all stars remain within their galactic homes. Some stars have crossed the boundaries of their galaxies, wandering alone in intergalactic space. Who are they? How can we find them? And what do they reveal about the history of the universe? Intergalactic stars, also known as rogue stars, are stars that do not belong to any galaxy, drifting alone in the vast expanse of intergalactic space. While seemingly forgotten, these stars hold complex stories of formation, evolution, and dynamic interactions between galaxies, helping illuminate the grand mysteries of the universe. One of the primary reasons intergalactic stars are ejected from their parent galaxies is due to collisions or mergers between two or more galaxies. When galaxies approach and interact, the intense gravitational forces not only reshape their structures, but also lead to fascinating phenomena. During these processes, some stars are pulled so strongly by one galaxy's gravity that they surpass the escape velocity of the other galaxy, being flung out of stable orbits into intergalactic space. Once ejected, these stars are no longer bound by the gravitational pull of any galactic system, becoming wanderers in the vast cosmos. Another common cause of intergalactic stars is interactions within binary star systems. In such systems, two stars orbit each other due to gravitational forces. When one star in the pair interacts with a supermassive black hole or another object of extreme gravitational pull, their orbits are disrupted. The closer star is drawn into the massive object, while the other star is propelled with tremendous force, ejecting it from the galaxy. This ejected star becomes an intergalactic star, embarking on a solitary journey far from its original environment. A striking characteristic of intergalactic stars is their remarkable velocity. Many of these stars can reach speeds of up to 1,000 kilometers per second, fast enough to escape the gravitational pull of their home galaxies and move beyond conventional orbits. With such high velocities, intergalactic stars traverse immense cosmic distances, sometimes traveling millions of light-years from their points of origin. During their journeys, they remain unbound by any galactic system, drifting through the mostly empty space between galaxy clusters. The existence of intergalactic stars not only highlights the complex dynamical interactions between galaxies, but also emphasizes the dynamic nature of intergalactic space. Contrary to the common perception of this space as a tranquil void, it is, in fact, a turbulent environment where objects like intergalactic stars constantly move, carrying with them stories of cosmic transformation and evolution. The detection and study of intergalactic stars are crucial for understanding the history and structure of galaxies. Astronomers use data from these stars to trace their origins and identify the powerful astronomical events that led to their ejection. For example, some intergalactic stars carry unique chemical signatures reflecting the environments and conditions within their parent galaxies. These clues allow scientists to reconstruct detailed narratives of the formation and evolution of major galactic systems in the universe. Intergalactic stars serve as a reminder of the universe's surprises and continuous transformation, revealing that even the emptiest regions of space harbor captivating stories. Their presence reminds us that the universe holds countless hidden secrets, waiting to be uncovered. By studying intergalactic stars, we not only gain deeper insights into galaxies, but also advance further in the journey of deciphering the vast mysteries of the cosmos. Discovering intergalactic stars is a significant challenge for astronomers, as they are often too faint to observe from Earth. However, advancements in telescope technology and analytical techniques have made it possible to track and identify these wandering stars in intergalactic space. These advanced methods not only help locate them, but also expand our understanding of the intricate processes underlying cosmic interactions. One of the most effective ways to detect intergalactic stars is through X-ray radiation. Although these stars rarely shine brightly enough to be observed in visible light, some can be identified through intense X-ray emissions. When an intergalactic star interacts with a black hole or a neutron star, matter from the star is drawn into the gravitational pull of the massive object, forming an accretion disk. This disk compresses and heats the material to extreme temperatures, emitting X-rays detectable by telescopes like the Chandra X-ray Observatory. These signals enable scientists to pinpoint the locations of intergalactic stars, even those millions of light-years away. Additionally, some intergalactic stars exist in binary systems that include a normal star and a black hole or neutron star. In these systems, material from the normal star is drawn into the black hole, producing not only X-rays, but also emissions at other wavelengths, such as infrared or visible light. The combination of these emissions generates signals strong enough to be detected from great distances. These unique binary systems not only help astronomers locate intergalactic stars, but also provide deeper insights into the dynamic relationships between stars and massive objects. Spectral analysis is another important tool for identifying intergalactic stars. This method measures the red shift or blue shift in the star's light spectrum, providing information about its velocity and direction of movement. If a star moves at an unusually high speed and does not follow the gravitational orbit of any galaxy, it is likely an intergalactic star. Using this technique, scientists can determine not only the current location of these stars, but also trace their trajectories, reconstructing the cosmic events that propelled them into isolation. The development of space telescopes and observational systems like the James Webb Space Telescope also plays a crucial role in discovering intergalactic stars. With its high sensitivity to infrared light, the telescope can detect faint signals from the most distant stars, even those obscured by intergalactic dust clouds. This opens new opportunities to study intergalactic space in unprecedented detail, unraveling more mysteries about wandering stars. Finding intergalactic stars is not just a story of technological achievement, but also provides profound insights into the intergalactic environment and cosmic interactions. By studying them, scientists can explore phenomena such as galactic collisions, black hole formation, and the distribution of matter in vast space. Each intergalactic star discovered is a valuable piece of the puzzle, contributing to the comprehensive picture of the universe's ceaseless motion. In this way, methods for detecting intergalactic stars not only aim to locate solitary stars, but also uncover foundational discoveries about the nature of space and the forces governing the universe. From faint X-ray emissions to subtle spectral clues, each signal we capture tells a marvelous story, shedding light on the mysteries of the cosmos. Intergalactic stars, or rogue stars, are not merely solitary stars in the universe, but also serve as critical witnesses, illuminating the history and evolution of the cosmos. Studying these stars not only leads to new discoveries about their characteristics and journeys, but also provides profound insights into gravitational interactions and the large-scale structure of the universe. Firstly, intergalactic stars vividly demonstrate the collisions and gravitational interactions between galaxies. When galaxies collide or merge, the immense gravitational forces involved can eject some stars from their original orbits, transforming them into wanderers in intergalactic space. By studying the trajectories and chemical compositions of intergalactic stars, scientists can reconstruct these collision events, revealing the formation and evolution histories of galaxies. For example, if an intergalactic star bears unique chemical traces from its parent galaxy, it can disclose the environment and conditions at the time of its ejection. Beyond revealing galactic history, intergalactic stars are clear evidence of the powerful effects of gravity on a grand scale. Gravity not only shapes the structure of galaxies, but also creates complex interactions between them. Stars ejected from their home galaxies are direct results of these gravitational dynamics. By studying the orbits and velocities of intergalactic stars, scientists can test the accuracy of galactic dynamics theories and better understand how gravity influences the formation and organization of the universe. Intergalactic stars are not merely passive entities, they also interact with their surrounding intergalactic environment, leaving significant impacts. Traveling at high speeds, these stars can create shockwaves in intergalactic gas clouds. Such phenomena heat the gas clouds, trigger complex chemical processes, or even initiate new star formation. These interactions can influence the structure and dynamics of the intergalactic medium, contributing to the formation of smaller cosmic structures, such as star clusters or protoplanetary systems. Moreover, intergalactic stars are essential tools for testing cosmological theories. They provide empirical data to evaluate theoretical models on the distribution of matter, galactic interactions, and cosmic evolution. For instance, the existence and number of intergalactic stars can confirm or challenge hypotheses about how dark matter and dark energy influence gravity on a large scale. These stars also help verify models of matter movement through intergalactic space, particularly in remote and less studied regions. Additionally, intergalactic stars help us better understand the nature and distribution of matter in the universe. These stars act as natural beacons, illuminating intergalactic regions that would otherwise be difficult to study. The light and radiation emitted by intergalactic stars enable astronomers to use tools like X-ray telescopes or spectral analysis to gather detailed information about their surrounding environments. In conclusion, studying intergalactic stars not only broadens our understanding of stars, but also provides invaluable insights into gravity, galactic evolution, and the intergalactic medium. These stars, though solitary in the vast expanse of space, are keys to answering critical questions about the history and structure of the universe. They are not just intriguing phenomena, but also bridges helping humanity move closer to comprehending the vast and complex nature of the cosmos.